Hi everyone, thank you for the attention. Today I'm going to introduce our work Paulihedral, a generalized blockwise compiler framework for quantum simulation kernels. This is a joint work with UC Santa Barbara, Amazon, and IBM. Quantum compiler is an essential component in the quantum computing system. Basically, it mitigates a gap between the application and device, and also it can optimize the quantum program for a better execution performance. Before we introduce the compiler part, let's first review the basics of quantum software and hardware. Here is an example of the quantum teleportation program, and we use a quantum circuit diagram to represent it. In this diagram, each horizontal line is a logical qubit, is a basic quantum data type. And to manipulate this data, we have a bunch of gates and measurement. Those squares are single qubit gates, and those vertical lines connecting two logical qubits are two qubit gates, and they are CNOT gates in this diagram. And those squares with an instrument panel inside it are measurement, and they are used to read data from your qubits. To execute this circuit, you basically apply gates from the left to the right. Now let's take a look at the hardware. On the left is a figure of IBM's 5-qubit superconducting chip. In the superconducting chip, one famous architectural constraint is a qubit connection constraint. And we can represent this architecture constraint in a data structure called the coupling graph. If we represent each qubit with a node and then connect those nodes if there are some physical wires or resonators connecting those physical qubits, and we can have a coupling graph in the middle. And the constraint here is that the two qubit gates are only allowed on those connected edges. For example, if we want to run a CNOT gate on Q0, Q1, it is doable. But if we want to run a CNOT gate on Q1, Q3, this is not doable because these two qubits are not connected. So as a result, one famous compiler path for superconducting architectures is the qubit mapping. So sometimes we need to insert some swap gates in the circuit to exchange the mapping and then make all the two qubit gates executable. There are also other quantum compiler paths. For example, the gate cancellation path. In this path, we can look for some gate pairs or even more series of consecutive gates that can be canceled out. And we also have such two-qubit gate block rewriting. Like we look for a bunch of gates at 2-qubit level and try to calculate its gate matrix, resynthesize it using fewer gates for better performance. And recently, people are looking into more and more detailed hardware information. For example, we can finally scheduling the gate execution of concurrent gates to mitigate crosstalk effects. And we have many more paths out there. If we summarize the design principle of these paths, they are either like application hardware agnostic paths like the gate cancellation paths, or they are trying to use more and more detailed hardware information like those qubit mapping and crosstalk mitigation paths. One direction that is less visited is, can we design deeper compiler optimizations with algorithm or program information? Naturally, if we are able to leverage the algorithm or program information, we can have deeper optimizations. But it turns out to be very difficult from the very beginning, how to extract such algorithmic information from the program. The key problem here is that the gate matrix size grows exponentially as the number of qubits increases. For example, for single qubit gates, we are basically dealing with 2x2 matrices. And for 2 qubit gate cases, we're dealing with 4x4 matrices. And for 3 qubit circuit blocks, we're dealing with 8x8 matrices. And in general, for n qubit gate, we have to process some 2 to the power of n by 2 to the power of n matrices. And the size of such cases is very, very large, and it soon becomes hard to reason about, analyze, synthesize, or decompose such matrices. That is why the previous work are mostly looking into the hardware side, not the algorithm side. So naturally, if we want to effectively extract something from your program, we need a high level, more abstracted, compact form representation of the program. It may be very hard in general, but it's definitely possible if we only target a specific part of the program. And simulation is our target in this study. Quantum simulation is a widely used algorithm design principle in quantum computing. First of all, simulating a quantum system itself is a very important application of quantum computing. And for other problems like the graph Qiskit, we can also encode the solution to this problem in the ground state of an artificial quantum system. In all these algorithms, we sort of need to simulate the time evolution of the real or artificial quantum system. As a result, one subroutine, which we term as the quantum simulation kernel, appear very frequently in many quantum programs. This kernel is to implement this operator, e to the power of IHT. T is a parameter, and H is a Hamiltonian operator of the simulated system. To compile this operator, you will see a very long gate sequence in your final circuit. First, you need to decompose your Hamiltonian into a weighted sum of polystrings. Here, W are some weights, P is a polystring. And I put the formal definition of polystrings here, but you don't have to memorize it. And instead, what I hope you can focus on in this talk is the program patterns, the gate patterns in those polystring simulation circuits. Here is an example. Suppose we are going to implement this exponential IWZZZ. I have 3 different circuit diagrams here. They look quite different, but they are actually equivalent. The only requirement is that we need to connect all these qubits using the CNOT gates in a tree structure. Here, I print out the trees of all these circuit diagrams. In the first one, we connect Q0 to Q1, Q1 to Q2, Q2 to Q3. This is a tree, and the Q3 is the root. In the second one, we directly connect Q0, 1, 2 to Q3. And the Q3 in the center is the root. And the third one, we have a more complicated tree structure. Q0 connected to Q2. And we have Q1 to Q3, Q3 to Q2. But it is still a tree. We can leverage this property to enable deeper quantum compiler operation for this quantum simulation kernels. In this talk, I will mostly focus on explaining the mapping part. Let's first take a look at how a conventional compiler will map this polystring simulation circuit onto a superconducting architecture. A conventional compiler will first convert the operator into a basic gate sequence using single qubit gates and 2 qubit gates. Suppose it is using this ladder structure with CNOT gates from Q0 to Q1, Q1 to Q2, Q2 to Q3. And we consider the left half, the left 3 CNOT gates. And the superconducting architecture we are hoping to map onto is on the right. It is a 2x3 lattice, and the current mapping is shown in this figure. To resolve the dependencies of the CNOT gates, we first need to execute the first CNOT. So a conventional compiler may swap Q1 up by one step. And after that, you can see Q0 and Q1 are connected. Q1 and Q2 are connected. So the first two CNOT gates can be executed. And then we need to execute the CNOT on Q2, Q3. So a conventional compiler may swap Q3 to the right by one step, swap Q3 to the right by another step, and then we see that Q2 and Q3 are connected. So the last CNOT gate can be executed. Now let's take a look at how our polyhedral compiler will do the mapping for this polystring simulation circuit. Instead of converting this operator into basic gates, we consider this operator as an entire circuit block. Recall that the requirement of the CNOT gates is to connect all qubits in a tree structure. So in polyhedral, what we are doing is to merge all the logic qubits into a connected subgraph in the hardware coupling map. For example, we can use a swap gate to move Q2 down by one step. And now we can see that Q0, 3, 1, 2 are in a connected subgraph. And now we can use this tree embedding we find to synthesize our CNOT gates. For example, we can have CNOT gate on Q0, Q3, and then do CNOT on Q2, Q1, do CNOT on Q1, Q3. And finally, the circuit we implement is something like this. It looks very different from the previous one, but since all the qubits are connected in a tree structure, we know it is equivalent to the previous one. Now let's compare these two different approaches. In a conventional compilation, we first convert this operator into some gates, and then we search for swaps for each of the CNOT gates in this gate sequence. And totally, we need 3 swaps here. But in polyhedral, we treat this operator as an entire block, and we only need to merge all the qubits in tree embedding on the hardware. As a result, we only need 1 swap. And such a compilation strategy can greatly reduce the swap overhead because we leverage the high-level information that, okay, a polystring simulation circuit can be implemented in arbitrary tree structure. What we can do with the polystrings is much more than just the mapping onto superconducting architectures. In Paulihedral, we first have a new programming language, a new intermediate representation, IR, based on the polystring operators. We call it PolyIR. Using this IR, we can maintain high-level information of the simulation kernels, and we do not need to reconstruct the high-level semantics by calculating the very large gate matrices. And our language is designed to accommodate symmetry preserving, error mitigation, parameter sharing, things like that. Basically, all the algorithm constraints of quantum simulations as far as we know. Upon this new IR, we're able to have new optimization process. We can have more aggressive gate cancellation. We can schedule circuit block at a very large scope. And we are able to adapt to different backends of different characteristics. If you are interested, please see our papers for details. To evaluate polyhedral, we select a wide range of Hamiltonians of real systems like molecules, Ising models, Heisenberg models, and we also generate some random Hamiltonians. And we also include UCCSC ansatz for variational quantum eigensolvers, and also the QoA graph ansatz. As you can see, by adding polyhedral compilation, we are able to have a very significant reduction in both gate count and circuit depths on superconducting architectures and also the fault-tolerant quantum computer models. And the overhead is quite small. We only need less than 5% of additional compilation time in the entire flow. Now we are working on adopting Polyhedral into Qiskit and some other industry compilers. Previously, most quantum equations are first compiled to some assembly-style gate sequence, and then compilers apply low-level gate or post-compilation strategies. But now we can first compile application to a high-level IR plus gate sequence, like this mixed language representation, and then we can have high-level compilation first before we apply any follow-up generic low-level optimizations. And also, quantum algorithms are not only about simulation, and we can have more high-level optimizations for other quantum algorithms. Thank you for your attention, and now I'm going to take some questions.